It's a great pleasure to welcome you all to this workshop held by TC222 in ISSMGE. My name is Magnus Rømoen. I'm the chair of TC222. Just shortly about the ISSMGE, it's the International Society for Soil Mechanics and Geotechnical Engineering. It has 90 member societies and around 20,000 individual members. ISSMGE is organized in 37 technical committees, where TC222 is one of the 21, which is organized under applications. This is the TC222 Council. I am joined by Jelena from the University of Birmingham in the UK, Michael from BRGM in France, Mats, which I'm working with here at NGI in Oslo, and Raymond, which is working for Geo in Hong Kong. We have a website, which is organized through the website of ISSMGE. If you want to contact us, this is the right place. Here there is a contact form. We also have a LinkedIn page and a YouTube channel. Both places you can just search for TC222 and the pages will be pretty easy to find. If you want to become a member of the TC, you have to go through your national member society in ISSMGE. We don't have the possibility to add you as a member ourselves. So far, there are approximately 50 members, so there are definitely room for more members of the TC. This is shortly today's agenda. I'm not going to go through the details. Jelena will inform you about this and lead the workshop. But we are extremely happy to have 3 very good speakers today. We are all looking forward to the presentations. So thank you so much to the 3 of you for saying yes for presenting today. The workshop is recorded and the recording will be shared on our YouTube channel afterwards. Here you can also find our previous workshop. We hope that everybody except the person talking or presenting can mute their microphone and switch the camera off. I think we have managed to set this up in Teams, so you're not able to share or talk, but we're not 100% sure. So please mute your phones and switch off the camera. We have approximately 300 persons who signed up for the workshop. And based on this, it's not possible for us to have open discussions, including every one of you. We have therefore set up a Slido page for questions that you can ask each of the presenters. So how to access the Slido page is given on the slide. You can either use the web address and the event code, or you can use the QR code. We will also share the link to this Slido page in the chat. After each presenter, we will use 10 minutes for questions, so please feel free to send in as much questions as you want. You can also vote for questions that other people has written into the Slido page, so that you can prioritize the questions that you feel is the most important. That was all the practical information. I think we're going to get started with the workshop, and for introducing the presenters and leading the workshop, I'm passing the digital floor to Jelena.
Thank you very much, Magnus. I hope you can hear me well. I'm going now to share my screen and the presentation, a very brief presentation that I have prepared for today. I want to thank everyone for joining, saying good morning, good afternoon, good evening, depending on which place in the globe are you currently. This is our second technical workshop on frontiers in research on digitalization in geotechnical and underground engineering. My name is Jelena. I am Associate Professor in Digital Engineering at the University of Birmingham, and within this core team, I represent the research. And our first workshop, or second workshop actually, will be covering research in digitalization, BIM, and digital twins in geotechnics. Why the research is so important? Well, we are all aware how diverse sources of data we have in our geotechnical projects in underground engineering. So this is truly a multidisciplinary field where we have to deal with not only different disciplines, different sources of data, different models, to understand each other and to support each other. And what is our goal is actually to start with this data and then proceed and research from collecting, managing, and visualizing this data to actually extract some information by modeling, analyzing, and interpreting this data. Moving forward to this pyramid of knowledge, from these analysis and interpretation, we always want to learn and to improve. And finally, we want to become wiser. So we want to generate models that are scalable, that are generalizable, that are shareable, and all this is very research intensive. You will all appreciate that digitalization is in engineering is overall a new, let's say, arena. Perhaps starting in last 20 years, and digitalization in geotechnical and underground engineering is even a bit let's say more recent trend. And if we look at the research published over past 15 years, we can see an increasing trend in research publication, journal publication in BIM for underground and underground engineering and tunneling. We can see that BIM for geotechnical applications, including slope stability, foundations, deep excavations, and so on, is also an increasing trend due to its obvious importance. However, a bit lagging between maybe BIM for tunneling. And if we look at the last demands actually for underground engineering, we know that our projects are not only required to be robust and cheap and delivered on time, but they must be risk-free and they must be sustainable. So this is something again that more and more will be included in research and education and also practice. And again, if we I analyze these papers that have been published in the last 15 years using natural language processing, and I created here Sankey chart using latent direct allocation, where we can actually see, even from analysis of the keywords or the topics of these papers, that at the beginning BIM was used for the design and maybe for construction. However, throughout the time, building information modeling and digital twins advanced in this pyramid of knowledge. So we are not only using them currently for design and assessment, but we see that adoption of machine learning and computer vision, and with digital modeling, of course, introduce new topics. First of all, we see that increasing trend on using BIM for risk management, disaster management, so far more holistic and complex problem. And in more recent years, also for automated detection, inspection, maintenance, and proactive maintenance of our underground infrastructure. Again, I'm repeating the importance of sustainability. So analyzing the published research on sustainability, we can actually see that, for example, again, this was just part of the management at the beginning. However, in period 2, many new topics emerge related to IoT data and sensing. So this is again this bottom layer of the knowledge pyramid. And in last period, we see a far more holistic approach when analyzing our projects, where we have some integrated geotechnical practices, digital modeling, and assessment of the environmental impacts. And all this is enabled or basically emerged due to increased digitalization in underground engineering. Just to sum up, we have plenty of challenges associated with digitalization in underground, starting from ground modeling of underground structures, BIM GIS integration, sensing, analysis and condition assessment, process steering, sustainability, interoperability, and IoT. you cannot see the slideshow. All right, so this is because I can see it on my screen because I have two screens, but let me just
see it, Jelena. I can see it.
Yes, so, okay, all right.
Yeah.
All right, but here I also come to the conclusion of my introduction why research is so important, because we start research and hopefully we bridge the gap between theory and practice and transfer these research findings from our theories to practical implementation. And therefore today we have three distinguished speakers who are going to address some of these challenges that I mentioned in my previous slide. Our first speaker is Professor Qianbing Zhang from Monash University Melbourne Australia. Qianbing is an associate professor specializing in geomechanics and tunneling at Monash University. He received his PhD from EPFL Switzerland and worked as a postdoctoral researcher at the University of Cambridge. He's fellow and chartered professional engineer with Engineers Australia. He's an editor-in-chief of the Tunneling and Underground Space Technology and served as the vice president of the International Society for Rock Mechanics and Rock Engineering. He was awarded Australian Research Council DECRA Fellowship. Additionally, he actively contributes to the committee members for Standard Australia and ISO standard, ISO TC222 on sustainable cities and communities. And to this, I would like to add that Qianbing is distinguished researcher and professor who is educating future generations of professionals working in digitalization in underground, and thanks to him and people like him, our community will go rapidly. I would like now to open floor for Qianbing, and we are looking forward to your presentation on a framework for integrated embodied carbon assessment and construction feasibility in prefabricated stations. Thank you very much. Could you,
Qianbing, Jelena? Can you hear me?
Yes.
Yeah, share my screen. Can you see my screen?
Yes.
All right. Thank you so much for having me. Good morning, good afternoon, or good evening, depending wherever you are. It is my great pleasure to share with our recent progress, particularly focus on the sustainability and digitalization. So the topic today is quite a wide, for the discussion purpose. So the work is mainly done by two of my PhD students and also collaborated with others, including Jelena. So the topic I'm going to cover today is mainly based on three. One of them is underground infrastructure, talking about digital decarbonizations and transformation. Now ongoing for digitalization and the sustainability for the management. So let's start with the first topic. So I believe everyone's clearly understand the importance of decarbonization in buildings and infrastructures. And all this week, until we have some literature review based on major on the policy guidelines and the standard actions to be taken by the different countries and organizations. So the majority of these organizations we listed here is already mentioned about the importance of this decarbonization in infrastructure. So I'm going to share with you some of the data we collected recently. I'm not quite sure this is exactly correct. Not if you have any errors or some mistakes, please let me know. So in terms of decarbonization in different sectors, so the left side is majorly showing you about different infrastructure sectors, which is majorly influenced or directly from infrastructure. So all these actually emissions, either from Sustainable Development Goals target or its contribution totaling those GHG emissions. So these two numbers there. Given this presentation will be recorded, I'm not going to read these numbers there, but clearly we can see the importance of infrastructure contributing to the sustainability of CO2 emission. So I will take it two data, for example. One of them is from UK, summarized by the ICE. So the total emission is there. We can clearly see the infrastructures have more than a half, so 59% of this emission coming from directly or indirectly from infrastructure. If we have further sub-sectors, so we can see most of them, among 5 of them, so transport is only one sector, is have still increased transport, which is not coming from the more investment on the transport, but also coming from the pressure from different organizations, particularly from the emission standard and rating system. So let's take a look at another one. So based on the Australia's emission numbers. So the total number is similar as the UK. What the difference is Australia has more categorized or break it down factors for different infrastructures. So the number here we can see similar and nearly 70%, so even more than UK, those emissions coming from infrastructure. And if we look at further of this data, we can see the transport is still the second largest sector to contribute to the emission. And the transport embodied carbon is even more than 50% of total emission carbon. So overall, we can see either from UK or Australia, infrastructure is contributing majority of this emission to the overall total emission. So in terms of emission, we have to talk about decarbonizations. So CO2 emission have organized by different those organizations, and also from one of this is the GCCA CO2 emission reduction potential. We can say up to 2050, the emission potential up to net zero. We have majority of the contribution from relevant. So we can see clearly most of them are relevant to our research. So for example, the highest one is potential would be CCST, so the carbon capture and storage. And the others, for example, the first one, efficient design and construction, efficiency in concrete production, all this is directly relevant to the infrastructure we're going to build. And also highlighted by the ISSMGE 2020, so BEAM or digitalization, including PS 2080, all this potentially be the manager tools for the calculation and manage the data, particularly from the whole life cycle. So not only about the carbon management, but also the cost. So we try to understand all this infrastructure construction from design, construction, and the operation stage, which means cover the whole life of the project. So in terms of the BEAM, we mentioned a lot at the beginning, particularly summarized by Jelena on digital transformation globally. So we can clearly see the globally, so most of the country already placed those BEAM or digitalization as mandatory for majority of the major infrastructure project. So we have summarized most of this standard implemented in the current major infrastructure project. And if you are already aware of, or you are trying to understand how BEAM will be influenced on your project design, so this would be provided some very draft design guideline. So in terms of all this design, particularly from digital underground construction, we have one paper, review paper, so covering the BEAM, machine learning, and computer vision in digital underground construction. So if you have any interest in underground construction technologies, so this can provide you some of the references, particularly from the best resources for you to understand more about digitalization. So the majority, as I mentioned, of the organization already implement digital and also decarbonization into the project design. Once we look at all this, and the majority of this, or most popular of the rating standard system has been summarized here. And in UK, Europe, and Australia have different standards. So if we summarize all this standard all together, because all standard we have different focuses, and we can have all this clearly to see, particularly since 2010, and the majority of this standard have different versions. Majorly, all the summarized in this table has been used for the infrastructure, not only for building. So all this cover different scopes, and the rating method also will be widely different. And assessment type is mainly depending on self-assessment or based on the third party to assess it. And the verification also depends on internal or external verified. And approach, in terms of approach, we basically is depending on the scope method we're discussing here. So we just roughly divide them into two different categories. One of them is majorly about scope based, and the other module based. So I will briefly introduce you more about how we're going to use different scope or module method for different infrastructure project. But once I talk about the life cycle project, the majority of the reduction potential or carbon reduction is mainly for the building construction, not only for infrastructure. Once we take a very close look of this underground infrastructure, the world's first underground railway station in London, actually Baker Street here, we can see it was built in 160 years ago. So if you look at the quality of the current those underground station, so it's even the same or even have more resilience behavior and it performed. So which means if we implement directly using the building information of rating system for infrastructure rating, they potentially will have different understanding or bring different of even errors to the rating values. So that's why it's important to use different standards and different digital tools to transparently manage the data. So the topic today I'm going to cover majorly to cover sustainability. Some of digitalization's meaning for your information only, because we have the first workshop organized last year, and we have another 2 distinguished speakers to cover more on the BIM part. I will give you briefly some information about the BIM, what we're using here, and the more information I'm going to cover will be on the digitalization on sustainability part. So the second part, I will quickly go through this part. So this is mainly to solve the problem interoperabilities for consideration about geo-integrated platform. So we call them, it's a centralized platform. So we mainly divide them into 3 different categories from the digitalization design based on different infrastructure types with different level details, then majorly consider about stability analysis, and then for the carbon assessment, eventually to optimize different infrastructure design. Once we're talking about digital tools or BIMs, always we're mentioning about level details, which means you have more information or more level of details, so the rich data or the rich information you will achieve. So in these studies, I'm going to share with you 3 of these case studies. Majorly is for the tunnel and the mud cavern stations and the prefabrication stations. If you need looking for more definition and classification of different the BIM model, so these 2 references are for you for further study. So in terms of different BIM used for the underground constructions, most of the BIM or underground construction at the moment are using as design BIM, which means we have geometric information of the structure, and then we have design. All this is based on parametric studies. I'm having here some videos demonstrating how we use the Revit and Dynamo to control how we implemented directly this parametric of AutoCAD model into the Revit model, eventually deliver the underground design. So this is a part of the as a design BIM we're using. On the other side, since some of the project has been finished many years ago, for example, if we have already built in tunnel is finished, so we can directly use a laser scanner to have the data or point cloud scan, then eventually develop the code to implement or transfer different point cloud data into the BIM. So this is also has been widely used for different existing project, which is normally called the scan to BIM. And the quality and now details really depend on the quality of the laser scanner and also the details information of the underground infrastructures. So this is just a demonstration of we're using VTC Victoria Tunnel Center for the demonstration how to use the scan to BIM. Now, once we finish the scan to BIM, so for existing tunnel, we only understand internal geometric information and other those monitoring tools. For example, we're using GPR radar to monitor the thickness of the lining or internal structure of the lining. Eventually, we're building those segment model based on the laser scanner and the GPR model, so that we can put together into the 3D geological model, then eventually design different project scale tunnel model. So I'm not going to introduce detail, but I have the project to introduce how we can use this model. So as mentioned, if we use a scan to BIM, we can also use it by using above framework, and we can use as design BIM. For example, we can define different objects because all this object will be assigned different material properties, and then further we have to consider them as geotechnical underground tunnel engineers. We must consider about geological information. So the second part based on the model-based collaboration, then eventually we cannot exactly call digital twin, but at this stage we try to integrate the physical model and also monitor data into the digital model, eventually to predict the potential failure or changes in terms of long-term changes deformation. We just use some simplifying the geological modeling. So for sophisticated model by using other 3-dimensional geological modeling is possible, but it will bring some interoperability issues because different software will have different formatting. So at this stage, I believe most of us are facing the challenges with having so many different sources or different software, but eventually which software will be selected for the study. So we bring a lot of challenges. So at this stage, we're using Revit again by using parametric, those script and Dynamo to control or build a 3-dimensional geological model. So basically, I have two different steps. The first one is majorly to build a geological model, and majorly based on the borehole information we have. And the second step, how you're going to directly implement or incorporate those existing beam model into this three-dimensional geological model. So this can be streamlined to directly using Revit. So the reason we are using Revit is because it opened also the script for the Python to integrate with different of the numerical modeling software. So I'll just quickly go through them. So this has been already built for existing numerical modeling tools. For example, I'm showing next one. So once we finish the first part of our three-dimensional geological model, so then we have to develop tools, which means we have to have the tool, for example, which call it exchange enable, which means we define different functions and different family types of the model. If in this scenario, it's triangular caverns, it's quite a complex structures with different supporting structures. And then eventually we have the automatic execution in the software. We're using this is the Flex 3D. And once we finish those calculation, all the post-analysis of visualization can also by using those exchange enable back forward loop to the Revit for the visualization purpose. So if we look at this actual applications, we can see directly we can using Revit or Dynamo to control all these design parameters, including the overburden, different overburden, and different lining thickness, and the systematic bolting or not, and the column spacing of this underground support, which give you already some parametric design information directly from the Revit. And by using this Revit, the function, the next level is how we're going to manage the data and how we're going to integrate the existing monitoring data. For example, 3 of the monitoring data of that project, actually monitoring starting from the project excavation and until near the end of the project, we can see the change of that formation can be directly integrated into the model. And the challenge at the moment would be, as mentioned in the beginning, so different to develop three-dimensional geological modeling, we bring additional challenges for building the interoperability between the beam model and the three-dimensional geological modeling. Particularly if you have very difficult ground conditions, such as those fault dikes, and which bring additional challenges for the interoperability issues. So it's not only about zero twins issues, but also the interoperability between different softwares. So I will be mainly introduce you about the sustainability part. The reason that I bring your attention to digitalization importance, because in terms of calculation of digital information, the value for the information we connected from digital tools will be directly used for the calculation of the sustainabilities. And mentioned at the beginning, so all the project or CO2 emission from infrastructure that is particularly important. If you look at this is Australian current or transport infrastructure investment, there are 124 major project, and 58 of them is in the pipeline. And in particular, within these few years, they are around 25% increased tunneling project. So the challenge at the moment would how we're going to integrate different digitalization and the sustainability, particularly on the resilience. So comparing surface and the subsurface conditions, there are some similarities, but meanwhile the subsurface have own challenges. If you look at the data we connected here, so this is all the current ongoing project in Australia. So for the visualization purpose, so this operation data is set on 20 years only. So for example, each project, for example, here we have this project, construction induced this emissions, this number, and the operation 20 years, we have this number. So the calculation of this one basic data from ES or ERS, and the unit is given here, and the calculation based on the scope-based method. And we can see on the different states in Australia, 3 states here, and 3 different of these infrastructure types, road, railway, and metro. So eventually all this project will contribute different CO2 emissions. So how are we going to make a decision? How are we going to use directly the very net zero project design, or are we going to use the resilience-based design, or the cost or dominating design? So all this is based on the complementary of each factors. So we cannot directly use one particular method. So mathematically, it's quite simple. If we have level details, very simple or very high information level, so eventually give you different CO2 emissions. I will introduce more on this project. So this is the 3 of the current ongoing project in Victoria. So if you're familiar with this Australian Victoria state, so we in 1971 to 1985, around 40 years ago, we only have this city loop. Most recently, we can see there are 4 projects have been planned or has been already finished the construction. So this is the length of tunnel. This particular for this suburb rail, this is 90 kilometers. The Monash University is located here. So once we implement digitalization or different technologies, for example, the modular construction or TBM tunneling, so all this we have to consider about how we're going to transparently calculate all this existing data, or how we're going to use existing or historical data for the benchmarking purpose. So at this stage, for example, we are using 2 of this scenario because the 1 metric tunnel here is a real tunnel with around 7.2 meter diameter and 9 kilometers twin tunnel with 5 stations. And the other ones here is Westgate tunnel. This is road tunnel and around 6.8 kilometers of tunnel. So there is no station for this, the road tunnel, Westgate tunnel. So let's have a close look at what other data look like. So this is 2 emission total numbers here based on the scope-based method. So this is scope 1 to 3. We can see the emission, the majority emission actually, in particular for this scope 3. So you can see this is scope 3 for metro tunnel, 18 for the tunnel, and the station is a 48. This massive concrete has been used to build this station. And for the TBM tunnel or Westgate tunnel, we can see this 71%, so which means the majority of this coming from scope 3. So what are scope 3 covering? So we look at here, scope 3 majorly include those segment lining and also building different of this casting concrete. And scope 2 is something we can have some simple demonstration. This is for schematic purpose only. So for the road tunnel, this is the actual scale ratio, 7.2 and 15.6. So in the entire presentation, I'm using these 2 as a benchmark or baseline for the calculation. So we can see for the other 2 parts, scope 1 by using different equipment, transport. Scope 2 is majorly for the operation, lighting, or ventilation purpose. So those 3 have the potential to reduce the emissions, but how are we going to reduce them? How are we going to calculate them more efficiently? So taking one of these 7.2 kilometers, 9 kilometers as an example, we can see all these already have a breakdown emissions. So embodied carbon internal is 1, and then it's 2 embodied carbon station is number 2, and then for the operation stage, this only for 20 years. So we can see the massive of this still in the operation stage. There are many other emission numbers. I'm going to give you more information how they're going to calculate these numbers. And if you are not familiar with this standard, you can have more information from those names here. And also we have the recently published paper. And majorly to cover 3 different stages from product stage, construction process. And then this is called the A1 to A5. This is also the easy to calculate. The B is using stage, and the end of life is also fun challenges to calculate or have all the data covering the life cycle of the project, because it takes around 150 or more years. Let's take a look at close. If we know all these numbers and based on digitalization or BIM model, we can easily have funded the carbon factor of each of these numbers and then have a takeoff of this number. Eventually, we can calculate all these emissions. So as I mentioned at the beginning, we are using parametric design for all the on-the-ground construction. And then functionalities in terms of this, we have developed this closed loop of this Revit-based parametric modeling. And at this stage, we are incorporate sustainability one. So this is standard we're using. So which means we can integrate all these 3 together. And then hopefully we can build and end of the project, we can build a digital twin for the project. So this is one we can easily to have different names for them for parametric control. So if we know this project very well, clearly in the dimension, then next stage would be how we're going to use different of the information. If we control the what is the same, and then we change different height, thickness, and change different interior structures, and change different reinforcement ratio. So easily we can calculate those numbers. This is normally called embodied carbon, and also can be easily calculated if we know this volume directly from Revit, for example. And also in terms of once we finish the design, our next stage is the functionality, which means if we select the last one here as the final design, now we can use the same framework we introduced previously. So this can also be parametrically controlled to eventually calculate the stability issues as well. So which means we cover not only about CO2 emission, but also safety, stability of the project. Some of the factors I believe you know very well in terms of construction simulation. So we're using this one for building the construction. So the detailed information is given in this paper. And also we developed a virtual sensor here. So if we have integrated modeling or monitoring data, we can directly by using those sensors to predict the potential changes or potential those risk areas. Overall, we usually use prefabrication station, but most of the project I mentioned at the beginning, the TBM tunneling. So this is quite a simple, or nearly the same as one I introduced for the prefabrication station. So if we select an LOD 400 example, if we know all this ground information or dimensions here, so that's next step, easily we can build everything together into the digital model. So which means we design this information and build a three-dimensional geological model, and to select different alignment and then control different diameters, decrease width, material, standard bolt. And then once we finish this model here, and then we can clearly see can be directly imported for the numerical modeling. And also we can use analytical solution or empirical study as well. So depending on which stage of project I design. And this stage, we're not using three-dimensional modeling, but just simply show you can be easily used three-dimensional modeling, but as shown here is majorly because this can be directly implemented into the software by using analytical solution. So the second stage majorly about how to select different concrete or different reinforcement ratio. So this is a lining we normally have. So the next step, once we have the quantitative information of all the lining thickness dimension, now we move to the carbon assessment, which means we this have reduced or increased or we achieve net zero or not. So this is covering overall the project. For the TBM tunneling, which have more stages than prefabrication stage, which means the beyond the stage, which means the TBM or other equipment can be reused or recycled. So this is standard is updated last year. So this is the latest version, 2022. So again, I'm not going to cover the details. Majorly, we're going to introduce you A1, A2, A3 is the same as embodied carbon, and is full transport of lining thickness depending on the trips and also different fuel use or different distance or vehicle type. And the construction is based on TBM or spoil removal. And user and end is still very difficult to calculate at this stage. If you have any data, we are happy to try to use the data for the calibration. And also we have done some analysis on the reuse and the recycle. So the paper has been under review. So this is the information here. So in terms of A1 to A3, it's the same as previous mentioned by using the prefabrication station, the same principle. And the most interesting part would be how you're going to calculate the TBM in this emission. So we understand TBM is driving different directions under different ground conditions. We'll have generate different driving direction, and also we'll consume different power and generate emission as well. So that's why entire study, I'm more interested on how you're going to calculate TBM. But to calculate TBM, so we can easily to calculate this carbon baseline for segment lining. As I mentioned at the beginning, different standards. This is we connect all the information public available from the standard or different countries in terms of different carbon factors. I mentioned if we know the volume, so if we know this carbon factor, we can easily multiply them. We have a strength grade, and then also we have some substitution materials. If we have, we have potential we reduce the CO2 emission. So this is will be available online. So I'm not going to cover details information, but we can see from A1 to A3, if we have a lower strength of concrete, definitely we have a lower this emission. But meanwhile, if we have lower strength, and the lower strength will potentially have this weak support design. And if we have all the internal tunnel diameter, we can see produced emission will be significantly different from 6 to 16. We can have seen the number of emission is more than 4 times. So if we know the diameter of the tunnel and we know the connected materials of segment, we can clearly calculate this easily. As mentioned in the beginning, the majority of existing project, we can also use scattered beam information, which means once we have beam information, we know all this quantitative volume, and when we know the carbon factors by using the parametric information, by either using Rhino or Revit or Dynamo or Grasshopper, for example, the parametric to calculate data to save a lot of time. So most of the existing standard or database also have the possibility or pathway to integrate with the beam. So now we have 2 different projects. Design one of them 7.2, and the second one is 15.6. For the first one, we can see the generated model is very quickly to know this is information. If we change different thickness of this segment, and the emission will be automatically generated as well. Once we change this to 15.6, you can see the diameter is quite larger, and then we can see emission numbers significantly also increase. So this can be also automatically calculated as well. As mentioned in the beginning, so once we know the distance or lining numbers or thickness, the transport distance, we can clearly say this is emission number. If we know the level detail 200, which means just tube, concrete tube. If we have level detail 400, so it cover more information. You can see this level, the higher level details of the lining or tunnel, we will have the number of total emission will be increased. And we do have a lot of this emission types here is given. So, and to the low level one, we majorly have the concrete and the spore removal. It's keep the same value in the level details 400 and 500. But if we have 500, we can see interior structure or the outer face is completely different. We can have more detailed information. So all this include A1 to A4. Now we look at the emission numbers for the analytical solution. As geotech engineering, we understand very well about by using different numeric modeling or use CCM or volume loss. So this is basically a very analytical, fundamental issues in underground design. So we know this information, we can easily to calculate the TBM driving direction and the TBM support information, and also we can calculate potential normalized convergence or change the support pressures. So all this information we can easily implement into the digital platform as well. So once we have a different diameter, so we calculate the diameter from 4 to 16, covering the majority of information of the tunneling. So we can see the embodied carbon emissions here, and also we have different factors of safety. If we have other factors, for example, the cost, definitely we can integrate them into the design platform. Now, once we finish the A1 to A4, that A5 construction one, so as mentioned in the beginning, if we know the TBM power, that we can generate emission as well. This is just a scenario to show you once we have different topography, which means all this will have different pressure or in situ stress. Once those TBM is driving in different thickness or different depths of this tunneling, so the power will be used completely different. So we calculate all this information based on analytical or empirical equations. So if you select a different empirical equation for different TPMs, eventually you will generate different powers. So let's take a look at how we're going to calculate them. So the majority of this TBM will have two different functions, token information. If you have a larger TBM, definitely you have a higher of the token numbers, and now based on different calculation method. So then we can calculate TBM in generated embodied carbon, and all this carbon can be categorized into different scenarios. For example, we calculate them based on most information about the thickness or the depths of this underground project. So in situ stress here is indicate the depths of the project. The higher or the more deeper of the project, we generate higher of this emission. So that would be quite make sense. And if we look at all the information from A1 to A5, so only the A5 is varied data depending on the depths of the project. If we have higher in situ stress, then we can see this excavation emission will be varied, which means material transport normally the fixed number for the construction, lining is also the fixed number, but excavation emission for project will be varied depending on the depths or the ground conditions, and also different types of rock and soil. So this is showing something different we observed from the recent study. So eventually we'll put all the numbers together to calculate or optimize data. So eventually I'll show you quickly the data here. So once we know the emission numbers from A1 to A3 or even to A5, if we know this is different, factor of safety or different cost or different stress information, or this one we only show you how we're going to identify those potential this baseline for the project we are designing here. I'll show you example we are having here. So the information we normally have for the project, we design the project, reduction would be there, but eventually for the operation and the maintenance, as I mentioned, at this stage, as particularly for the geotech engineers, we understand there are multiple hazards there. A lot of hazards will influence the 150 years design life, All this will generate more emissions. For example, if we have normal conditions that have crack, damage, and failure, all this will induce potential emission number increased, and different normal conditions. Now, this is a standard one we calculate. Then after each stage, because we need to retrofit it, or we have to replace or additionally to repairing this concrete lining, it will generate additional CO2 emission. And until the failure of the project, probably we have to think about how we're going to find a solution to replace this entire tunnel, for example. So this will eventually induce more emissions, and we can see the number is even 4 times higher than the designer this emission. So which means the importance of integrate different service life into the project design. So in this project, I try to introduce more on integrate different digital twins and CO2 emission numbers. And for the next stage is the most important part, how we're going to conduct the performance of resilience, then put them together, how we're going to use optimized data. So based on measure on the performance of the project, if we have longer service life, definitely we have to put a stronger concrete, but strong concrete will induce more emissions. All this is conflict factors. So how are we going to optimize also the potential directions we can work on? So eventually we put all this monitoring data prediction, because we are doing geological engineering, geotech engineering, we can predict the potential changes after 150 years. This is why geological or the underground project is significantly different from surface building, because underground information will be changed. We have to monitor, predict the potential change over the life cycle, longer even than the surface building. So put it all together, so we introduce the platform covering digital twins, then calculate the CO2 emissions, and then monitoring sensor for back analysis, put them together and as interactive platform. I believe this is all the slides I have. If you have any further information, I have some published papers already in this slide. You can have more information. Thank you so much.
Thank you very much, Qianbing. This was an impressive presentation. Also, I would like to thank our audience for posting very interesting questions for you. Now we are going to have approximately 10 minutes long Q&A session. I will start with the most popular questions first. And the most popular question on Slido is, how do you deal with the ground-related uncertainty shown in the modeling workflow?
Yeah, this is quite a common question we are facing as well. I believe this is majorly for the reference design. For the detailed design, it's have to consider all those ground information clearly. And parametric modeling cannot be directly used for detailed design. For any, the chain length and detailed design has been directly used. So that's why, particularly for the academic stuff, we are majorly driving the direction what we are working on, but not on the very detailed design. I believe consulting engineers will have more the power to control this detailed design information. Yeah, we are working on, but challenge is very much, yeah.
Yes, absolutely. And the one general question I will leave for the end. I would like now to pass some technical questions, which are related to diversity of data, as I mentioned at the beginning, and the software preferences. First of all, for the ground modeling, do you prefer, or why do you choose Revit Dynamo over some 3D modeling software like Frog or others? And also, are you modeling semantics or soil parameters, or only geometry of the soil?
Yes, that's very interesting question as well. We do use different 3-dimensional geological modeling, including Leapfrog, GeoPy, open source 3D geological modeling software, which plays the significant data processing. This is also need a sophisticated geological knowledge as well. And at this stage, a lot of researchers also working on data-driven the characterization of site and geological modeling, but majorly focus on the soil properties selection instead of building 3D geological model. The most interesting part to me, because we have to put all this 3D model into numerical modeling. So in terms of computational efficiency, we couldn't directly import the whole or the entire project length into the three-dimensional modeling, numerical modeling. That's why we just selected normally 100 meters by length. So within this dimension 100 meters, so easily we can confine or identify potential these challenges, and even we can manually to update the information. In terms of behavior of the model we're using, that is one of the functions by using Flex 3D. We can use not only geometric information, but also use material parameters by using Python to control those parametric workflow. If you use different software, probably these functions may have some differences.
Yes, I do agree. I mean, we are both working in the same area, and the method is, let's say, software agnostic. So, but we choose perhaps some Autodesk software due to convenience, ease of implementation of parametric models. However, this could be done with other softwares as well. I would like to now read two maybe rather comments than questions, and then relate to one question. Soil Cloud posted that geotechnical engineering isn't only structure, it's also soil mechanics. In situ or lab and test, and this is not mentioned, which is appreciated. And in addition to that, it's not only structure and mechanics, but it's also geology, basically, and genesis, and so on. Can you add perhaps more? I know that you're covering only one part, and again, geological modeling, this will be actually a subject of presentation of our third speaker, but can you maybe mention something about interactions of different digital models, and that we do not have to perhaps to have all the information in one 3D digital model, that your model was for the purpose of calculation, maybe of structure rather than geology?
If I understand the question well, so the question would be asking more why we focus on more soil behavior instead of using structure analysis information.
It's opposite. You are focusing more on structure, and maybe not modeling so much in detail geologies, geotechnics, soil and soil behavior, and so on.
All right, yeah, that's very also as well the good question. So based on the information we are working at the moment, so we did also thousands and 10,000 of parametric modeling by using different behavioral materials. Of course, selecting different, even simple constituent model, and for different of the geological conditions, then we achieve completely different of the stress condition. So that's why we try to build the benchmark or the baseline for the project design, and all the design information we're using is quite widely used the method, even like CCM or volume loss. All this is based on the structure design and the mechanical behavior of soil or rock. It's not directly based on the structure information, but also the geo information. So if you are reading information about the volume loss and also convergence confinement method, all this is interaction between the supporting structure and the in-situ stress conditions or soil or rock behavior. And if you recall, I have one slide showing TBM performance emission, so which is majorly dominated by not TBM itself, but also majorly dominated by different depths or different mechanical properties of these ground conditions. So which means we try to identify more factors from a structure point of view, then eventually how we're going to make the right decision, because all the decision eventually is dominated by both of the factors, not only soil or rock, or the soil or the structure, sorry.
Thank you very much. And a question related again to soil, posted by Florent Robert, who is lead of working group ITA working group 22 on beam and tunneling. He asks, how do you deal with the carbon footprint of excavated materials?
Yeah, that's just also a very good question. So this is majorly to the use we are doing. Just to use the existing database. So for majority project in Australia we are working on, that is the site has been already identified for dump this spoil removal, which means if we know this distance away from that excavation site, we can roughly to estimate the distance and the fuel or this is emission generated by different vehicles to transport this spoiled soil down to that site. So in terms of this detailed information, so the paper we actually submitted under review already covering this information. So we use a case study of these two projects I mentioned in this presentation. So I hope this paper can be accepted for recently, so you can have some detailed information for your calculation. But that is A4, stage A4 have this transport of the information, so covering not transport segment lining, but also transport delivery those excavated materials to the identified site.
Thank you very much. A last quick technical question and one general question. Quick technical question is, does the resilience calculation include all the tunnel hazards like squeezing, spalling rock, burst, etc.?
Yes, that is also an interesting question. So at the moment, we consider nearly all of the factors, but the most important part to me at this stage, we're working on rock tunnel. So that is a rock squeezing is a more important information, because change of the squeezing information or the creep information of the rock and the lining will be different. So if we use the same creep rate for rock or for lining, eventually they will probably induce additional pressure from the rock on the lining. So which means we cannot use the current pressure to estimate the performance of the lining over the next 50 or 100 years. So we have some creep tests and also develop this creep model to predict a certain area. So this cannot be the generalized method, but it can be also directly for the specific area if the rock has the creep information or not. And also again for the rock burst and hazard of others, we also have the second factor would be deterioration of the lining, the concrete itself, because concrete itself probably have less than service life than the rock. That's why the deterioration ratio of the lining is also important. We are using European standard at the moment. And the next factor would be the water issue. So water is how we're going to calculate potential once we have lining or cracks happening on the lining, so we can use existing underground water and the water flow rate to predict the potential of this volume directly flow from this underground. So this stage we're using those three factors predict this resilience curve.
Thank you very much. And a last general question, maybe if possible, some very answer to the point is, what do you think? What keeps country from making BIM technology mandatory?
This is not the area I'm particularly working on. I believe the other two speakers will directly answer the question. But based on my understanding, literature review, because all the project at the moment will becoming asset. So for the asset of the project, we, as at least from the client point of view, we need to to have the data is properly managed. So in terms of all this management tools or digital twins, BIM or the digital twin, I'm not quite sure which terminology it's referred to from each country, but I believe this digital twins will provide a very valuable, at least from geo or tunneling point of view, that will provide a very clear or visible for the next stage of the performance prediction and the management.
Yes, I agree that this is a matter of maybe a lack of education and maybe clearly communicating all the benefits that BIM and digitalization can bring to the countries. If education would be implemented properly in the systems, and if this would be communicated properly to politicians, probably this is something that I guess will also happen in the future. Well, Qianbing, thank you very much. This was very insightful. We are going to collect all the questions, and maybe we will going to share them with you to maybe give some more specific answer for those that I didn't manage to cover. And thank you very much for your really insightful talk. I would like now to move to our next speaker. And our next speaker is Richard Ho from Geo Hong Kong. Richard is a chartered geotechnical engineer and has been working for the consultants and the Hong Kong government for over 18 years He obtained his bachelor degree at the Hong Kong University of Science and Technology, a master degree in applied geoscience from the University of Hong Kong, and have a law degree from the University of London. Mr. Ho is currently geotechnical engineer at Slope Stability Division of Geo Hong Kong. He also worked at ARUP and MTR Corporation on various civil and geotechnical engineering projects. He is one of driving forces in the information technology and innovation technology development in Geo Hong Kong. And lastly, but not least, he is part-time lecturer in the Technological and Higher Education Institute of Hong Kong. So Richard has been on front list of digitalization in geotechnics for nearly 2 decades, and I'm sure that his talk is going to give us a lot of breadth in what has been happening actually in practice and how these developments have been adopted. Richard, can you please share your presentation?
Okay. Okay, can you see my presentation here?
Yes, I can see your presentation on the screen.
Okay, thank you. First of all, thank you, Jelena, for your introduction. I'm Richard Ho. Nice to meet our fellow members here. The topic 3D geotechnical information infrastructure is one of my recently completed IT projects, and we look at the digital chain or digitalization from another view. In the following, I will briefly introduce our project here. Before that, let me introduce the background of our GeoINT strategy. Innovation and technology have always been the Geo priority in enhancing our service and local geotechnical practice. We have been taking a steering role in technical development work for slope safety in Hong Kong. Here are the 4 pillars supporting our INT development. To keep it short, they are fostering a vibrant culture of INT, nurturing talent within Geo, strengthening technological collaboration across different stakeholders, identifying and applying technologies for application, implementing suitable INT engineering practice. And here are the 6 key INT technical areas covered in GEO. They are robotics and automation, digital technology involving BIM, IoT sensor, and other ones is artificial intelligence. We are developing machine learning for landslide prediction and novel technology about the new material and remote sensing, robotic solution, and digital chain. My presentation will be divided into 3 parts. Part 1 is 3D integrated geotechnical information infrastructure. We call it 3D G-Info. The second and the third part are about our new initiative, a 3D geotechnical model, 3D GM, and Geo digital chain. 3D G-Info was launched in October this year and disseminated to our industrial partners and government departments. One thing I must emphasize here, 3D G-Info is an open platform. It is an online platform. That means everyone, if you have our user account, you can log into 3D G-Info and repeat the demonstration that I'm going to show you below. You can repeat it by yourself. Everyone can see the same information on this online platform, and it is tailored. And it is tailored with our government, Hong Kong government open data policy. So what is 3D G-Info? It actually goes beyond the function of information management system only. It will act as a backbone for real-time digital chain platform for managing Geo key assets and services. 3D G-Info has greatly enhanced the efficiency of our daily operations by 3D visualization and spatial data searching. The new features are particularly useful for us during the landslide emergency service. For example, we can appraise the surrounding of the landslide site quickly and to assess the residual landslide risk. Sorry. 3D Geoinfo actually relies on 3D spatial data provided by our lands department to develop a full 3D visualization. It also continues to act as a central repository database. With the advancement of 3D technology, we can capture, create, and visualize more 3D models, including landslide site and territory-wide airborne LiDAR survey results. BIM models of our completed slope upgrading works or mitigation measure under LPMIT are also incorporated. Regarding real-time monitoring, it can serve as a backbone for GEO digital twin platform for hosting various information systems, such as GEO Smart Platform, Busan Drainage Tunnel Monitoring System, Smart Construction System, and subsequent smart facility, which I will give you more background in the following. So this is the new user interface about 3D Geoinfo. You can easily access to the slope information. For example, the basic slope geometry, consequent to line category, maintenance record, and the maintenance responsibilities of each slope in parallel with this 3D digital map. Now I'm going to show you more on how it looks like. This is an online platform, and you can search via a map, just like a Google map. And when you close up to a feature of your interest, you can open different layers. For example, pirate log layer. And we, in Hong Kong, we have divided the slope into different portions. We call it subdivision to delineate the maintenance responsibility. As I mentioned previously, 3D Geoinfo now can contain and visualize the landslide model created by LiDAR data and photogrammetry technique. We have established an operation procedure with our internal survey team for carrying out immediate LiDAR and photogrammetry survey after any significant landslide reported. The landslide 3D model will then be uploaded to 3D Geoinfo directly. Now, I would like to show you another video. In this video, it shows the New Heng Road, which is one of the biggest landslides in Hong Kong during the bad rainstorm in September this year. As you can see, when we input the 3D model into 3D Geoinfo, we can manipulate it from all directions, all angles. What is the benefits of this? Using the spatial model, 3D spatial model, it can facilitate us to review the residual risk of the landslide impact and help us to make decisions for follow-up action and more information for subsequent landslide investigation. Here is another example captured in current 3D Geoinfo, which are those landslides occurred in this year. For this 3D model, we have utilized both LiDAR and photogrammetry techniques. The LiDAR technique can help us to eliminate heavy vegetation and delineate the existing ground profile. For the mesh model created by photogram, this allows us to easily identify the feature characteristics and assist in later engineering analysis, such as depth mobility assessment. And this is one of the examples that we use the LiDAR data to compare the slope profile before and after the landslide. The technology helps us to appraise the scale of the landslide and assist us to make decisions on providing suitable emergency works on failed slope. The mitigated measures such as rigid and flexible barriers installed on natural terrain, which also put it inside the 3D Geoinfo. As you can see, we can put the BIM model, BIM model of the rigid barrier and also for flexible barrier into this 3D mapping system. And we can also input the barrier energy rating, design impact velocity, and retention volume of the rigid and flexible barrier that can facilitate our asset management and facility management. In order to develop such a 3D mapping system, we need 3D spatial data. And novel technologies is one of the key for us to collect the 3D spatial data. In this slide, you can see there are some handheld device. We call it handheld 3D camera and LiDAR scanner. They actually are customized by GEO. They are used for capturing point count and images for creating 3D realistic mesh model. The benefits of this device is that they are handy and easy to use, and they can actually mount on the smart robots for site inspection at dangerous environments, such as landslide site and confined space. What is the good thing of them is that they provide the 3D model for us, which are the major or important ingredient in building a 3D scene in digital twin. So the next topic is about the development of the 3D geotechnical model. In parallel to the development of the 3D geoinfo, we have also tried to create 3D geotechnical model. We call it 3D GM of Hong Kong by using available GI data, about 300,000 GI borehole. Unlike a geological map, the 3D geotechnical model would emphasize on this usage in engineering application. And this figure actually shows the schematic idea on the generation of the different soil layers of the geotechnical model. The model is based on interpretation of GI records with similar engineering properties, such as SPD and saddle and design work head level for power foundation. And this model could facilitate planners and engineers to appreciate the general ground condition on engineering application for preliminary planning, design, and schematic analysis, etc. of geotechnical works. I'm going to show you an example of the model for typical use of the 3D GM on foundation design. Imagine this 3D GM can be viewed by all practitioners online. You do not have to worry about the software. Anyone have internet access, you can view and see this ground profile and have an idea of the work head level in the area of interest. An additional user interface, as you can see here, we call it Workshop Viewer. It is actually a user-friendly platform that allows us to further manipulate the 3D GM. As you can see, we can cut cross-section from different angles. And in the coming year, we are going to upgrade this Workshop Viewer. Hopefully, we can add more useful functions, for example, measurement and calculation of volume and overlay other spatial information on it. We are doing this development work at this moment. So I move to my last part. That is the 3D actually GEO digital twin. Our digital twin platform for smart barrier is available on mobile device to facilitate our colleagues on site during the emergency service. I would like to take this opportunity to demonstrate some of the key features of this platform to you. And this one actually is a smart barrier installed near the Queen Mary Hospital in Hong Kong Island. And in this online platform, you can view the 3D scene and BIM model of the Queen Mary rigid barrier. And the little point here is actually some of the IoT sensor. When we click on it, we can see the sensor detail. And for example, this is a camera, and we can see the real-time situation or condition of the camera. And more than that, we have a function to capture an image if we have a special interest on it. So apart from this existing smart barrier, we are going to install more such IoT system on the completed barrier under the LPMIP program. The system will be integrated with BIM model for future assets management. And this slide actually shows a Bosan drainage tunnel. We have physically installed the monitoring system in this tunnel. And more than that, we actually have an online platform to monitor the groundwater condition, the groundwater level. As you can see, the groundwater level is continuously monitored by pressure gauge installed on the subvertical drain and piezometer of the slope above the tunnel. And this platform allows us to view the real-time data through the internet. More than that, we are now kick off a pilot study, LAMDI, Smart Surface Drainage Monitoring System. This project is to install ultrasonic and laser sensor on slope to identify any blockage of channels or accumulation of soil debris in cappage, as shown on this slide. The sensor will transmit the data to GEO server via LoRaWAN, and any blockade will be indicated and notified to the maintenance agent for reminding them to do follow-up action. A user interface has been developed to monitor the data of the sensor in the drainage system, and the consumption level of the battery will also be shown here, so that it can alert the maintenance party to replace the battery. Currently, we have installed a 3-stop site for trial, and the system is equipped with digital camera, which is used to verify the situation during this trial period, and the data is stored in cloud platform, and that means we can access to the real-time information anytime online when we want it. Lastly, you can see we have actually gained a substantial experience on development on IoT system for our operation, and we will continue to apply it to more of our new features and new facility. The picture shown here is one of them. It is our new public works central laboratory, and we are going to install a series of IoT sensor and automated monitoring system. And we are going to build up a new online platform to incorporate all the sensor data in this online platform real time, such that we can monitor and view the situation of and the condition of this new facility. And it is actually under development. At last, all of the above smart platform or IoT system they will be incorporated into a single dashboard, as shown here. We call it our geo-digital twin. We want to have a single platform allow all of our colleagues to access on this online platform and switch between different platforms and know the actual condition, real-time condition of our facility, rigid barrier, the new central laboratory, the tunnel, etc. And we hope that one day we can do some bi-dimensional control. We can switch off the facility or the sensor inside the facility. And hopefully we can do more than that in the future when the technology can allow us to do it. That's the end of my presentation. Thank you.
Thank you very much, Richard, for your really insightful talk. We really learned a lot, and it's impressive practical implementation of all very emerging digital technologies. We have a number of questions posted on Slido, so most of them are technical questions. So I will just go and try to, let's say, we'll try to answer them as precisely and quickly as possible. First of all, can you tell us something about the accuracy of your 3D model?
I think you are referring to the 3D geotechnical model.
Yes.
This one. We are using a new 3D spatial format to present the geotechnical model. We call it workflow layer. It is one of the less CDF format. And what actually is this format? It is like a Minecraft. We are building up some square or rectangular block. Just like a game, and we put all the blocks together. And actually, we can make a resolution in more detail. But at this moment, we want to make it a 1 meter per meter, 1 meter square resolution. I think we can actually make it to a more fine resolution, but it will affect the performance of the online computer, the online performance. Because our model, the objective of our model is for foundation design and for preliminary design only. So we stick to 1 meter per meter, 1 meter at this moment. And actually we can make it to 0.5 or even 0.1. But the trade-off is that when we put it online, bear in mind the performance of the user, the end user may have a less smooth or fluent experience on it. But there is no technical limitation on the resolution actually.
Yes, thank you very much, Richard, for answering this question. And it's very interesting, actually, how you present your GIS-based platform and how you also relate to BIM that Qianbing has presented in our first presentation, because obviously these are two very different scales, where on GIS we have more, let's say, rough or less detail or less fine modeling. We can always relate this GIS to more detailed BIM models with more information. And regarding some details of the geological modeling, how does the 3D GM model geological surfaces and ensure features such faults and unconformities are adequately accounted for? And also, how do you take into consideration the uncertainties in 3D GM?
Thank you for this question. I actually have listened to a similar question before. First of all, I must emphasize that our model at this stage is just a simplified, one of the simplified model. As you can see here, the yellow color is actually the soil, and the pink color are rock level. And the blue level in between actually is some SPDM value 100 and 200. They are based on the foundation design criteria at this moment. It is a very, very simplified model. And we have actually considered to make it more complicated. And we have asked some IT firm to write some Python script for us. And we can actually tailor-make and customize the block inside. We call it the voxel cell. We can replacing the voxel cell inside. What does it mean? If I have a predefined a fault zone within the model, I can actually like drawing a line inside the model and replace the yellow line, the yellow one by one by another fault zone. I can fill in the model by another material. This is one of the approach that we have considered to make it more complicated to represent the fault zone or more complicated geological structure. We hope that we can have more trial and some application example in the future. With respect to the uncertainty, it is the question we have received before. At this moment, we want to make it simple. As you can see in this slide, apart from showing the 3D geotechnical model, you can also see the 3D borehole, the column, how many boreholes we have used to create this 3D geotechnical model. We do not expect the practitioner will use this model for detailed design, project-based design. We expect that practitioner will, or even the public, will only use this model for preliminary idea, feasibility study. So on the right-hand side of this model, you can see there are a lot of boreholes, and the uncertainty of the model will be low. However, on the right-hand side near the sea, you can see there is basically no 3D borehole at all. So we do not want to make some illustration or confusion to the user. So we want to leave it here to let the user know that there is no borehole, and don't trust on the right-hand side. And you can trust more on the, sorry, I put it on opposite side. The user should not trust on the left-hand side because there is no borehole data, but they can consider to use the right-hand side. Below the building, there are many borehole data, and it is obvious we do not input any interpretation, and we try not to confuse or give illusion to the user. So we deliberately do not set some uncertainty here in this model.
Thank you. So this is regarding geometrical, let's say, accuracy, but how about soil properties? Which kind of the soil properties do you actually have in your 3D GM model?
At this moment, no. We only have the characterization of the soil type in this model. But we are talking to the developer. The fossil cell, it is a new kind of 3D spatial data. And the good thing is that they can input value on it. Actually, the GIS industry, they are using voxel for temperature and other like a water flow, etc. They are using the fossil layer for another field. But we see the opportunity is that we can actually input the soil parameter inside the fossil cell or fossil field. In the future, we hope that we can input those soil parameters. Hopefully, we can input them at least by this type of soil or rock. We can input a type of soil parameter in them, and then hopefully we can do some statistical analysis. Because the strength of this GIS data, like in 2D, we have raster, it is a square. We can do some beautiful statistical analysis. We are expecting in 3D, the fossil layer, they can actually help us to do some statistical analysis. But the bad thing is that this technology is so new and we cannot do a lot at this moment. But we hope that when the technology advance and improve, we can input more soil parameter and data in them, and hopefully we can do more analysis through this platform.
Thank you very much, Richard. I will have a very quick technical question, and at the end, another more general question. So we discussed a lot about geology and geotechnical modeling or soil modeling. How about safety structures? Are they also attributed in your GIS-based platform, or are you rely on it based on the BIM models and the link of BIM models with BIM models?
We are lucky in Hong Kong because not only our office or our department are working on the 3D spatial data. In the 3D GInfo, we are actually using many different spatial data. The building, as you can see here, they are actually prepared by our lands department. Our lands department have different techniques to build those more 3D building model. For example, they have UAV during UAV and create some photogrammetry model, the mesh model, realistic mesh model, and some of them they have some specialists. I think they are specialists. They are actually building up some 3D object for each building, and they are not exactly a BIM model, but the beauty of our platform is that if we have a web model, IFC model, we can input them in this platform. So the good thing is that if we have the spatial data from one party, we can put them there. And if we have BIM model, we have our photogrammetry or point count model, point count data. We can all put them into this ArcGIS platform. And I would say we are lucky. The beautiful building here are not prepared by us, are prepared by lands department. But for the terrain, it is prepared by our department. Actually, we have spent some effort to do territory-wide airborne LiDAR, and we are using those LiDAR data to build a terrain model territory-wide, covering the whole Hong Kong area, and they build up the terrain of our 3D model.
Thank you very much. And my last very question, which will have probably a very short answer, is will the landslide data be open to overseas practitioners? And what software do you use to create this digital platform?
To my understanding, for geotechnical practitioner, we should be able to open the platform to you. So when you have the user right to access our platform, you should be able to access the landslide model as shown here. And we have and our primary objective is share the landslide data and other 3D data to our practitioner. So in the future, when you have the user account and you can actually access and view this landslide model, and we will create some function for practitioner or user to download at least the LiDAR data and other BIM data. Hopefully we can allow them to download it. But for the mesh model, because of the size, if you are really interested, you can send some email to us and we can consider a more efficient method to allow you to get the data. So the last question is about the software that we used to build this platform. I think it is not a secret, and I can say it here. We are using the ArcGIS, and on this online platform, we have built up a little bit complicated online cloud platform. We have a lot of server on the AWS cloud, and we are using ArcGIS Enterprise for publishing the senior and the GIS layer on the online platform. Of course, behind the scene, we have prepared the data by ArcGIS Pro, which is a desktop application, a software. And why we choose ArcGIS Enterprise? Because the beauty is that we can share the information in an online platform, and other users, as long as they can access to internet, they do not need to worry about the software license, and all of them can view the same information as I demo here.
Thank you very much, Richard, for your extremely insightful presentation and for answering all the questions. We will be very happy to share with the community maybe more details on how this data can be shared, how they can get in touch with you, create this user's account, and hopefully get data for research or just for increasing our practical experiences in, because unfortunately we know that in Hong Kong this year you had a lot of landslides, and this knowledge can be used to be maybe more proactive for some other areas in the future. Thank you very much. It was great pleasure having you as our speaker. And now we will move to our last speaker. I think you should be able to see my screen now. Our last speaker is Dr. Georg Erharter, and he is an engineering geologist at the Norwegian Geotechnical Institute. He holds a PhD in civil engineering from the Institute of Rock Mechanics and Tunneling of the Graz University of Technology, where he investigated the applicability of machine learning for geotechnics. Today at NGI, he is working with all aspects of engineering geology and geotechnics in both research and practical applications, always tries to apply the latest technology like BIM, remote sensing, and machine learning to solve the big challenges in our field. And I'm going to end this with saying that Georg is definitely a rising star in digitalization of underground and geotechnics, and we are having big hopes for his contributions in the future, but starting today with a presentation on developing scalable and generalizable data structures for BIM ground models and talking about chances and challenges. Georg, the screen is yours. Please, we are looking forward to your presentation.
Thank you very much, Jelena, for the very kind introduction. So yes, welcome everybody. Today I am going to talk a bit about data structures, information modeling, and information structures for BIM ground models, and chances and challenges that we are facing with doing that or with implementing these structures. A short outline of my talk. So first of all, I want to talk a little bit about preceding work, what has been done in this direction before I got to work with this. Overall BIM structures, where can we imagine a BIM ground model in the context of bigger projects and of bigger BIM frameworks. What is an information model? That was a crucial question that also that boggled my mind for a while. Chances and challenges of information models and information modeling in ground modeling will be addressed then in the end, and in the middle part we will talk about challenges of the actual definition of objects and properties. So let's start with the preceding work. Information modeling has been going on quite a while. And I think one of the first very relevant contributions was coming from this IFC tunnel working group, where you can also today find on the web this final draft for the requirements analysis report from 2020. I think, as far as I know, it stayed with the final draft, but this final draft contains a lot of interesting information. And they established some very basic ideas about information models in ground modeling and in BIM modeling, and they also define sets of properties that are currently being implemented in the new IFC scheme. So this working group was being active also beyond 2020, and for example, if you look into this GitHub repository, you can actually see that there is quite a lot of action going on where they are trying to now implement developed data schemes in the newest IFC versions. So this was one of the first things, and then building on that to a large degree, I want to mention the work of the DAUP. The DAUP is the German, the Deutsche Ausschuss für Untertagebau. So it's the German branch of the International Tunneling Association, and they have a dedicated group on BIM in tunneling that was formed definitely before 2019. But in 2019, they published the first recommendation, very general one on BIM in tunneling, which is also available on the web for free and in English. And this, at the point of 2019, gave a very good overview of this field of BIM in tunneling. When you read it today, it's still very interesting and relevant, but keep in mind, this is for almost 5 years in the past. Things have changed since then. But what has happened, that this working group was very, very active, especially during Corona, and they worked out and published a whole series of recommendations, so a total of 5, throughout 2020 to 2022. And I personally was involved in the third one. So the third one is dealing with the model requirements for ground modeling, for BIM ground modeling. And I guess most of you are not German speakers here, but most of these, or I would say 2/3 of these recommendations are available in English so far, and soon hopefully all of them will be available in English. However, the one that I was involved in, the BIM ground modeling recommendation, that gives a very broad overview and also gives you a certain guideline for a ground model and for data structures for a ground model, this is available in English already. So much for the preceding work, and I want to then, as a next step, hop into the topic of information modeling. And when I started to deal with this in more detail in 2020, I was working a lot on construction sites. I was working in very practical applications, and to me in the beginning, this was a very fancy thing. So information modeling, this was not what I was doing on the reality of the construction side. There it really was hands down work, you know, but information modeling sounded very intimidating, and actually a long time I haven't had an idea what this was about, but I thought this is interesting, this is new, we should engage in this. And for that reason, I will ask the same question to you. What is information modeling? Please join this Slido poll. So before I launch the actual question, you have a few seconds to scan the QR code or to join via the Slido event code. And yes, some people are in there already. Good. Then I go to the next step. So what is an information model? It's a quiz. You have 40 seconds time, and choose one of these 4 answers, and let's see what your state is about information modeling. A bit stressful with the timer, I know, but it's like that. 8, 7, 6, 5, 4, 3, 2, 1, 0, and the time is out. Okay, so no one said that an information model is a specific file type. This is correct, yes. I don't know how many it actually were, but some people said that an information model is a software application designed for handling data. We usually deal with information models through specific software, but the information model itself usually is not a software application. The third one is an easy one, so that's obviously false. The information model is a term used in statistics for describing an average value of a set of data points. That obviously is wrong, but the majority seems to have already quite a certain understanding of what is an information model. So it's an abstraction that represents the structure and relationships of entities within a certain domain of information. So this is correct. And I think, yes, we have a winner. One was very fast, but another one, the second place, was also very, very fast. So congratulations. Yeah, so this is one of the formal definitions that you can find when you Google and look into information modeling. And so I just read it through. So an information model is a representation of concepts, relationships, constraints, rules, and operations to specify data semantics for a chosen domain of discourse. This is correct, I think. This corresponds to how I understand it now as well, but I still think this is very abstract. And I think for people working with practical engineering problems, this still sounds very, very far from reality, because the point is that information modeling is very relevant for practical engineering. And therefore, we will have a closer look into what is information modeling for us in a few slides. Before that, let's have a look into the overall BIM structure. So when we are looking at a project and the project is being executed in a BIM-based way, we are usually following a certain hierarchical structure of models, objects, and other concepts. So when we go through this figure from top to bottom, and the very top, we usually have a certain coordination model. So we have to have one model that combines a lot of different disciplines. And the coordination model, for example, this could be the overall BIM model for tunnel XY. Then a level below that, we have discipline models. And there, for example, what is the most relevant one for most of all of us is the geotechnical model. So the geotechnical model would be one of the discipline models that feed into the overall coordination model, but there might be others. So depending on the project, there might be a dedicated tunnel engineering model. There might be a model for, I don't know, electrical installations and all these kinds of things. The discipline models we can usually subdivide either contextually or geographically. So if we divide it contextually, then we divide it into, as I said, like a geotechnical model, electrical installation model, and these kinds of things. But we can also divide it geographically, and this might be necessary in very large projects. I don't know, let's, for example, the Brenner Base Tunnel or something like that. So these huge projects, there it's not enough to only subdivide our BIM model into different disciplines. We need to subdivide it into different construction lots usually. Then we have domain models. So at the level of discipline models, I would say we also have domain models. And there a very important point is that the BIM models are actually filtered version of the domain models. So I guess some of you have been modeling with things like Leapfrog before. There is other applications like Move, and ArcGIS also to a certain degree produces BIM domain models. What we do not want is to basically dump the whole information of the domain model into the BIM model, because for most involved parties, there is not much use in that, and that just overloads the BIM model. So the discipline models are filtered versions of the domain models. Below the discipline models, we then have object groups, for example, the advanced documentation in general. Below that, we have objects that could be the tunnel phase. And below that, we then, for example, have a geological mapping part. So if we're mapping very, very detailed, and we want to say that this phase consists of several parts of different geologies, then this could be a sub object. And usually these structures today, they are predefined and project specific for every individual project. So even though I told in the beginning, there is the DAUP guideline, there is the ITA, the IFC tunnel working group, we have not found a common understanding or a commonly working structure for this kind of setup. Let's dig deeper into the BIM ground model, and on a very conceptual overview, we would structure the BIM ground model itself into a factual data model and into an interpreted and into further interpreted models. So on the one hand, we have factual data such as drilling, soundings, etc. And on the other hand, we are having interpreted models that are usually based on these factual data models. And looking into more detail into the factual data models, I want to make a little bit of advertising for NGI. So the factual data model is a collection of all the factual data that we are dealing with in geotechnical engineering. And I mean, factual in our discipline is a bit of an ill-defined word anyway, because in the context of ground modeling, I would call a borehole log factual. But in the end, even a borehole log is interpreted, of course. But I think most of us that are working on these projects agree that a logged core profile can be called factual. So all these observations and all these, let's say, low-level interpretations, they go into the factual data model. And for example, what I'm bringing up here, so the NGI advertisement is that, for example, NGI has launched and is now also commercially selling the Field Manager, which is a software that allows you to compile and collect in a very nicely structured way all of this factual data. There is other ways of doing that as well, but in the end, to create a factual data model, you have to have a data structure, you have to have a way of compiling all that information. And then the base, or the factual data model, is then basically the base for everything that is coming above or beyond that. So the interpreted models that we are then generating for the practical projects, because for the practical application, the factual data alone is usually not enough. We have to interpret the factual data into higher level interpretations of the ground. And so when we have an overall model area, there is different ways of basically segmenting this model area depending on the question that we are following. And so when you look at this figure, what you can see is that the total model area, just in a generic example, depending on what I'm after, if I'm after the geology, the hydrogeology, or the geotechnics, it can be segmented into different parts. So from the geological point of view, maybe I would only discriminate between two geological units: the sedimentary cover, I don't know, some fluvial sediments, and then the bedrock of a certain kind. But maybe I would have a very detailed structure of a fault zone in there. From a hydrogeological point of view, I would rather characterize and segment my whole model area into different permeabilities. So I would have a hydrogeological unit for the top layer, I might have one for the intact bedrock, and I might have one for the fault zone plus its surrounding. And then from the geotechnical point of view, there might again be another subdivision, because there I might differentiate between the sedimentary cover. Maybe there's a weathering zone on my bedrock, and then I again have the intact rock and the fault zone. So depending on what I'm after, my ground model is containing a different segmentation of the ground depending on the overall goal. And this can have all kinds of model types, basically. So here I only have the geological, hydrogeological, and geotechnical model. But just recently I had a discussion with a student who also pointed out that you could also have like an archaeological model, which is not wrong. When you think of areas in the world, such as Italy, for example, where there is a huge amount of archaeological facts in the ground, then you might want to segment your ground model according to where there is more or less archaeological findings in the ground. So coming back to the question, what is the information model? In the end, the information model is about the definition of objects and properties for the discipline model of the ground. And so we're not talking about the coordination model, we're talking about the discipline model, we're talking about objects, and we're talking about properties for these objects. And the consideration behind the information model is generalizability and scalability. So the information model that we develop, especially in these working groups like DAUB, and also information models for, let's say, public rail and road authorities, they should work for a lot of projects. They should not be made for a single project, because then they're not usable for the next one. They should be working for a lot of projects. So finally, what is the information model? I would say in the very simplest case, it's just a table. And I would have really appreciated if someone put it like that to me a long while ago. So information model, in the end, it's not very fancy. It's not very special. It's actually just a table. You can imagine it as a table that relates objects on the x-axis and properties on the y-axis. And the objects, there might be a hierarchy. So as you can see here, for example, there might be objects and sub-objects, like, for example, an object might be a drilling, and then we might have a drilling interval as a sub-object to that. And then we are having properties, and we are assigning these properties to the objects however we see fit from a technical point of view. And this by itself is not very hard to understand, I would say. So it's about defining objects and sub-objects and properties and building a relationship between all of these entities. And when you think back to the definition of the information model, so it's about defining relationships between entities and their properties, then we fit that completely. So this might look easy now. And I would also recommend you to have a look at the DAUB data model that is being published alongside of the recommendation. But also what I want to point out is that although the structure is easy, so properties and object definitions, that can be done. It is a certain challenge to define these objects and properties. So when we define objects, as I said, the goal is to be generalizable and scalable for many, many projects to come. And if I am working out these these object definitions, then I'm generally dealing with a trade-off between abstraction and generalizability, where I don't want to have objects that are very, very fine-grained. So I generally don't want an object for, let's say, for example, a seepage test, the plate load test, the pumping test, the overcoring test, and so on and so forth. But on the other side, I also don't want to just have one single object that is called test, because the more fine-grained my object structure is, the more objects I will have, but also the more objects I will have that I really don't need in most projects. The more coarse-grained, so the more abstract my object structure is, the less objects I will have, but I need to assign a huge amount of properties to the individual object to be able to actually use it for anything. So to be able to use the abstract object test to represent seepage test and overcoring tests, I need to assign a huge amount of properties to this object to be able to actually use it for something. And so what we are usually trying to is to find the golden ground in the middle, where we are having object definitions that work for most projects quite well, that can scale and generalize quite well, but that are also not too abstract. Kind of the same goes for the property definitions. You don't have to look at this table in detail. This is basically the same as was published by the DAUB, just a part of it. We are defining properties by property names, data types, units, and definition of the properties. And we're grouping them into property sets. And there also we are facing a certain trade-off between we don't want to miss important properties for certain objects, but we also don't want to overload the objects with properties. And that generally is a challenge because for most projects, we need very specific properties to be able to represent the necessary information well. So I now want to put you into this position of defining properties for an object. And the task is that we now want to make a data structure for the object geotechnical unit. So you can see here the geotechnical unit, or actually you can see several geotechnical units. And we define the object geotechnical unit as a volume in which the mechanical behavior and other design relevant characteristics are characterized by geotechnical parameters. And the question for you is, which properties do we need to be assigned to these volumes? So which properties do you think are necessary that we can actually work with these geotechnical units, not just in one project, but in many projects? We again do this in a Slido-based way. This is now it's not so stressful as before. Join the poll and just submit your suggestions for properties into this word cloud, and then we will see that there are hopefully a bunch of properties are going to pop up. So again, the question is, we have geotechnical units. Geotechnical units are volumes, homogeneous volumes of ground. And the question is, which kind of properties do we want to assign to these geotechnical units? And we see quite some things popping up here. The more people are typing, I've learned that this Slido preview of how many people are typing is not very reliable, but let's wait a bit more. Yes. Also, if you find some properties to be very relevant, just go ahead and submit them again. Obviously, the UCS is very relevant for many people. Okay. So I will just keep on posting things here. We cannot go through everything anyway, but I will start to discuss it a little bit. So it's quite interesting. I would say most of these properties in the months and months of discussions that we've had in these working groups, they popped up at some point anyway. So let's maybe look at the very big ones first. Strength, UCS, and thickness. In principle, I agree, yes. So strength parameters, so these high-level properties that describe the mechanical parameters of this unit, they are of course very interesting, and there can be many cases where we actually need to assign these. The issue can, however, be that the uncertainty is kind of a problem, because an issue that we generally face is that when we assign these very specific parameters, and I see a lot of them here, so like the E modulus, the UCS, the friction angle, the it's getting more and more. As we assign these very specific properties, we are also starting to kind of, let's say, represent a false certainty about what is going on, and then it is starting to be a challenge, especially when we're having a higher amount of uncertainty. We maybe don't have many investigations available. Then these very specific properties can be a challenge. But in general, I agree. So this big group of direct mechanical properties is, of course, very important. Then let me just see. The thickness, for example, is an interesting one, because thickness, I also see geometry here and things like that. So thickness and geometry is interesting from the perspective that these volumes, they have a thickness. These volumes, they have a geometry. And so the question is, if I have a property that is describing the geometry that actually is already present, isn't that a bit redundant? But I personally agree with that. So I agree that some properties, for the sake of convenience, they can be there to represent the geometry a bit better, because when I have this ground volume, I can measure the thickness at any point, of course. But for example, if we're dealing with sedimentary layers with a constant thickness, it can be very practical and convenient to have a property that is called thickness, because then I just need to click onto the ground volume and then I will get the thickness immediately. So these things, they can be done. What else do we have here? Yes, the same goes for area, and then more, let's say, high-level things like uncertainty and these kinds of things. It then definitely also always depends on how you actually want to represent this. So uncertainty, this could be just basically simply a text that says, I'm very uncertain about what's going on here, or you can find a more fancy method of actually communicating the uncertainty. Very nice. Thank you for all these submissions. I need to go on here. So just I'm starting to close up here. So this is how we have dealt with the issue of this geotechnical unit in a exemplary project, and that is kind of the trade-off that I wanted to talk to you about. So having these geotechnical units, I would say we basically have two main ways of addressing the properties for these units. Either, as many have you suggested, we can assign direct attributes such as density, friction angle, cohesion, and these kinds of things. And we can do this if we have a high investigations density, if we have well-known conditions, if we have a high resolution model, then this can be done. On the other hand, for example, if we have deep tunnels or we have a high uncertainty because we don't have many investigations because it's a, I don't know, feasibility study or something like that, then it rather might be the case that we need to assign whole ground a distribution of different rock mass types, for example, or ground types. So we might specify that in our project we are having, I don't know, we expect to have 5 different geotechnical units, and in this specific volume we expect 50% chance of finding the geotechnical unit 1. We have a 20% chance to find geotechnical unit 2, and so on and so forth. So with this way, we can address the issue of uncertainty in a bit of a more quantitative way. And we don't risk that someone opens the model and thinks, okay, this volume 400 meters below the surface has a friction angle of 37 degrees, and that is exactly how it's going to be, because that always is basically the threat that we are facing here. If you're interested into this more, we have a paper, or I've written a paper on that, and alongside of that paper, you can also find an IFC file where you can click yourself through that ground model. You can check out the properties that we have assigned to it. Everything's just kind of generic, but I think it's still quite interesting. And if you want to look at the IFC file, I recommend something like BIM Vision to look at it. Yeah, so my talk is called Chances and Challenges, and I want to close with chances and challenges because I think data models or information models, they have their pros and cons. So they are a great base for communication in challenging projects, because I think one of the main advantages is that if I engage in a challenging project and I'm defining a data structure in the beginning and I agree with everyone on the data structure, then everybody knows exactly what to expect from the final model, and there will not be any bad surprises that I produce a ground model which the client actually didn't want. So I can only recommend, before you start actually with your ground modeling, define what you want to model, and this basically means define a data structure. BIM in general, I think one of the greatest advantages of BIM is that it forces our community to be a bit more standardized and to think a bit more in a streamlined way, because I think we lack this in general, that everybody has their in-house solutions. They work great for whatever they do. But if I want to compare 5 different tunnel construction sites to each other, I have a hard time, because every construction site uses their own data models and their own concepts and ideas. And BIM helps us to reduce this uniqueness, so to speak. And for the project in general, the early development of a robust data model helps to save costs over time, because a lot of the additional efforts that we face, especially in planning projects, is that people plan around things that are either useless or missing. And if we define a robust data model early, then this pays off in the long run of a project. These are upsides, but however, we also have some downsides. So what we generally face as a challenge is that defining a robust data model at the beginning of a project, that costs money or that costs time, and time is money, and our clients are usually not used to that. So we are used to be basically easing into our projects, and the costs increase over time. And there we face a different condition, where that now we have a lot of costs in the beginning and they are starting to flat out over time. So that is usually a bit of a challenge when we engage in new projects. Another thing is that the ground in every project is unique. And I still think that we are probably never going to have the one data model that does it all for all of ground engineering, because geology is just very unique and ground engineering is very unique. And in some projects, I don't know, I'm dealing with squeezing conditions. In others, I'm dealing with natural gases. In the third one, I'm dealing with swelling minerals. We have all these very specific use cases, and finding a data model that does it all, I personally have a hard time imagining that. It can be problematic if we use BIM and conventional planning in parallel, and we see this, I think, in many parts of the world right now, that more and more our clients are transitioning into model-based planning and work, but in many cases they want this to be done in parallel or in addition to conventional planning. And then, of course, we might get some troubles when we have a BIM model that has the geometry plus the information inside the model, and at the same time we're having 2D plans, because then everything is kind of redundant, and there is, of course, a certain threat that information from the BIM model does not correspond 100% to the information in the 2D plans, because it's just a lot to produce, and in the process of producing all these documents, there can be mistakes and things just happen. So this is a problem right now, that this parallel work of BIM and conventional planning that might interfere sometimes with each other. And lastly, what I think, especially in ground modeling, what is a challenge is the lack of the suitable visualization software. We can produce the very nice ground models, and they have a good information, they have good geometry, but to directly transfer them into 2D sections as we are used to, and that are also very rich in information and that are very visual means of communicating ground conditions, there is still a lack on that. With that, I would say thank you, and I am open for any questions.
Thank you, Georg, very much for this. I would call it lecture rather than presentation. It's very important to bring everyone to the same grounds, because at the end of the day, BIM should be interchangeably used across the globe. So it's very important that we all have same understanding of how we define and model, and then later share the information and create some knowledge out of it. We have very interesting questions posted on Slido, and as in previous presentations as well. First question is about the uncertainty. Soil parameters varies a lot in 3D volume. How you handle this? Will it not be very complex model, specifically when adding a lot of parameters? And a similar question also, how to handle uncertainties of parameters in 3D models and how to handle interpretation between, for example, 2D information from the sampling. So it's both about uncertainties and difference between 2D and 3D.
Yeah. So I cannot fully answer this because as far as I know, especially in onshore applications, we have not found the final answer for how to deal with uncertainty. We have different, also we need to differentiate between different aspects of uncertainty. So I would say the one that is, it's not being done in many projects, but still it would be, I would say, more or less easy, is to deal with the geological uncertainty. And for example, boundaries between geological units, you can, as a geologist, you can estimate what kind of uncertainty is related to them. You can do this in a mathematical way, you can do this in an experience-based way, and then in your BIM model, you could model different boundaries. You could have like the most likely boundary, and then you have like deviation boundaries, basically, that have a certain distance to that. The same goes for the geotechnical properties. We can assign characteristic geotechnical properties, and then like the upper and lower boundaries of these properties. So we can assign all of this as properties to the models. It gets a bit more tricky when we deal like with sampling bias and these kinds of uncertainties. So the operator bias. There, to be honest, I don't know how to deal with this right now beyond having properties in the model that basically describe this issue of operator bias. And in 2D versus 3D, I have to say that what we always need to keep in mind is, or what I find a bit interesting, that this uncertainty topic really feels like it popped up a lot since we started to deal with 3D modeling. But it's a bit of a weird situation because in every 2D section that ever was drawn, this is exactly the same, has exactly the same kind of uncertainty as in 3D. So a 3D volume boundary is as certain or as uncertain as every 2D line in every section that ever was drawn. So there is not much difference between 2D and 3D, actually. Yeah.
So I do agree that this is the topic not of digital modeling. Maybe the question for us is how to visualize uncertainty. And I also agree that there is a difference between geological uncertainty and soil variability. So maybe the question for us is how best to store this data and visualize this data in 3D. A bit more specific question is how do you deal if a parameter with 2 or more characteristic quantities has to be specified because different limit states have to be considered? I mean, this is a very specific question, so I'm not sure whether you came across it in your practical applications.
Have not faced that exact situation yet, but I mean, the thing is that right now you can assign as many properties to your model as you want. You can have a property that is characteristic value 1, 2, 3, and then the other fact is that still, and I think we will not move away from this very fast, that when we deliver a BIM ground model, we always need to deliver a report that explains what is going on in that ground model. And I don't see a way around that basically right now. And there, if there is a need for multiple characteristic values, then I would say just assign multiple properties, give them a unique name, explain in the report what actually is in the model, and you can do that. Yeah.
Yes. Thank you. Next question is that, or maybe a comment even, a model for one project might not be fit for purpose for another project. Better to make specific model for a given project than a general one. So I think that this is actually the difference in thinking between practitioners and developers, because practitioners, yeah, but please comment on this, because I face this question a lot.
Yeah. Absolutely. I think that the state right now is that these information model proposals, like I have shown here, and like, for example, the DAUP has published, these are proposals. So these are not structures that basically are rigorously to be implemented. They should rather give you a proposal for how one can do this. And I definitely agree that in the specific project, it makes sense to adopt a more specific structure. But for example, this whole concept with geotechnical units, with geotechnical synthesis models and these kinds of things, that just makes sense. So right now, I would say rather see these things as guidelines and adopt it specifically for your own projects. Yeah.
Now back to your introduction of several recommendations that you have worked on or contributed to. There is a question that what are your thoughts on the recommendations of the AK 2.14 according to the Fachmodell Baugrund?
AK 2.14 Fachmodell Baugrund. Not a lot. I'm right now not very familiar with that, but please send me an email and reach out. Then I'm happy to share my thoughts on that.
And maybe last question from me is, so of course we are here presenting and we are having around the community on BIM and the digital twins for geotechnics, but at the same time like geological societies are also developing their 3D models. So my question is how these two feed into each other.
Yeah, I hope they do. So I think a general challenge right now is that we face a lot of parallel development, and we have a lot of groups, as you say, geological societies and BIM groups and so on and so forth. As I've experienced it when I was engaging in this work in the DAUP, that we had people like Jonas Weil, for example, who is very active in the IFC tunnel group. And he tried to harmonize the efforts of these different working groups into each other. So I think in this whole field today, whoever is working on these structures, they should really make an effort to check if there is parallel development going on, and if it's basically not already been developed, or if there is points where one can harmonize it. At some point, we will find the equilibrium, I guess. But right now, there is a lot going on in parallel.
Yeah, yes, different, let's say, professionals, but also in different disciplines like tunneling, mining, geotechnics. Again, we are all solving very similar problems, yet adopting slightly different approaches. So I think that the future is actually making that effort in synchronizing everything, exchanging knowledge, and coming to that wisdom that I mentioned at the beginning. But yeah, we have hard work to do to get there.
Absolutely.
Thank you very much, Georg. And I would like to thank you, Richard and Qianbing, for a really insightful presentation. And I'm sure that our guests on the online will also go and to their daily work with lots of impressions, lots of thoughts, lots of new ideas. At this point, I would like to invite our chair, Magnus, to give some closing remarks.
Thank you, Jelena. Just trying to share my presentation again. Okay. First of all, a big thank you to Qianbing, Richard, and Georg for 3 very good presentations. I really enjoyed the last couple of hours listening to these presentations. And also thank you, Jelena, for guiding us through the workshop. It's been really, really interesting. It is time to round off, but it's first we have some more information about the future plans for the TC. We are having a new workshop in the spring. We are discussing the led team for this workshop, and we are very open for suggestions and wishes from all of you. So you can either write here in the chat, or you can contact us through the contact form that you find on the webpage. We also have the feedback from a former member survey that we sent out in the spring. So we will of course look at the comments we got back then. When it comes to the European conference in Lisbon in August next year, there will be a TC meeting during the conference. I think the room booking that we got was during Monday, but we have to go back to you when it comes to the final details around date, time, and place. We haven't got everything from the organizing committee in Lisbon yet. Originally, we were also planning to have a workshop, but I think that we have ended up with probably not having a workshop. And the main reason for this is the limitation in the amount of people that we will reach out to. We see that having a digital workshop that we can also make a recording of, it's much better for us when it comes to reaching as much people as possible. We haven't made the final decision here, but I think we're not going to have a workshop. What we want to do is that we want to have some kind of social low-key event during the week of the European conference. Go for a beer, something like that. But also here we have to come back to you concerning the details and the arrangements. That was all for this workshop. We are very happy for the large participation, and we hope you all enjoyed the 3 brilliant presentations. And then I'll just say thank you and goodbye.